In my day-to-day job, I often work with molecular dynamics simulations. I see them mainly as a professional tool, but sometimes I'll run a simulation just to see what happens. So basically, I play around with them a bit. So it wasn't very long until I wanted to make my own program that's optimized to basically playing around with these simulations. And if you are seeing this video, it means I finally got around to actually producing something. Let me specify what exactly it is that I want to achieve here, besides just playing with colorful balls. I want a program that acts more or less like a molecular dynamics simulation that runs in real time. You also should be able to interact with the simulation in real time. Additionally, since I have a VR headset laying around, I want to see if I can make the whole thing in virtual reality to create an immersive interactive experience. Just from my real-time requirement, it is clear that most sophisticated methods are out of the question. In theory, some Hartree-Fock level simulation with small datasets might be feasible, but a virtual reality requirement will probably confine me to a game engine for now, and I don't want to try and import external packages into my game scripts. I could also myself implement the Hartree-Fock solver and integral evaluation from the ground up. In fact, in the last video I started talking about how one can quickly evaluate the integrals that are needed for Hartree-Fock, and if you don't know the Hartree-Fock method, don't worry, it's really not relevant for this video. But I do not like this approach for two reasons. Number one is that I haven't finished the final video on the integrals yet, which I would like to do before I apply the knowledge from these videos in other projects. And number two, I doubt that my code will be particularly efficient. The scripting language is probably something I have not a lot of experience with, so I doubt I will be able to write efficient code with it. I'm just a humble physicist and I think my code is reasonable most of the time, but I never really had to squeeze a lot of performance out of my code so far. These considerations leave us basically with just force field methods, and I have decided to go with the simplest possible method, the Lennard-Jones force field molecular dynamics. Let me explain. Here we have a fairly accurate energy landscape of the hydrogen molecule, calculated from more sophisticated quantum chemical methods. For the interested among you, this was calculated using the FCI method with the CCPV-QZ basis set. The x-axis is the distance between the two hydrogen atoms, while the y-axis shows the energy for each distance. In theory, we would just need this curve to generate fairly nice dynamics, since the force acting on the coordinate is just a negative gradient of this very potential. Sadly, calculating this curve on the fly is too expensive for our purposes, but one could explore pre-computing these curves for all kinds of different species. You just have to remember that there are a lot of possible pairings in the periodic table. However, our approach is simpler. We assume that all pairwise interaction potentials take the form of a Lennard-Jones potential, which is given by this formula here. We have two parameters to adapt the potential. Epsilon is the depth of the potential valley and sigma is the distance at which the potential is zero. This location is not really special for dynamics, but sigma is also related to the equilibrium distance, that is the distance at which the force vanishes. Using the parameters for the hydrogen-hydrogen interaction, we get the following curve. It looks pretty bad, right? But remember that the goal isn't to be scientifically accurate here, but to just be close enough to the real thing. And I guess for my purposes, even this horrendous fit can be considered good enough. I found a body of work that tries to give reasonable Lennard-Jones parameters for a range of different atomic species. These values are always given just for the interaction of an atomic species with itself. So how do we figure out the potentials between atoms of different species? If we have the parameters for a species I and another species J, the interaction parameters can be derived by applying the Lorentz-Berthelot rules. Since sigma is loosely related to what you can think of as the radius of the atom, repulsion gets really strong when the atoms are closer than the sum of their radii. For the epsilons, it's not so straightforward to interpret without some background knowledge, so I will skip the reasoning here. but rest assured that there is also some physical intuition at play. Now we need to calculate the functional form of the force and figure out how to calculate it efficiently. So far so good. And it is fairly easy to see that you can pre-compute the term sigma over r to the power of 6 and then use it once as is and once as a square. We should save at least a few CPU cycles, I hope. The method chosen for integrating the time steps is also quite important. I don't think we can afford a high-order integration scheme like Runge-Kutta 4th order, but the bad energy conservation properties of the simple Euler-forward scheme make it quite useless for this task. I will go with velocity worlet. The error scales with the square of the time step, which is fairly usable. With the theory now all out of the way, we can start thinking about the implementation. Since I want a VR experience, a game engine with included support for it seems like a good idea. I have heard of Godot before, so I'm trying it out for this project. It's also free and open source, which is always a plus. To start a Godot VR project, you just need to activate some OpenXR related settings in the project settings. After that, a VR player can be built by adding an OpenXR origin node, an OpenXR camera and 2 OpenXR controller nodes. Then you also need to provide some boilerplate code to initialize the VR interface. And that's about it. You can now at least visit your scene in VR. I would like to see where my hands are when I am in the game, so I added some small cubes that follow the tracked controller position. So now it's time to try it out. Everything seems to work fine. Of course, it is a bit ugly right now, with the environment being an endless grey void and my hands being Vantablack cubes and all, but these things can be fixed. To combat the endless void, I just added a simple plane as an anchor point for my reference. And to drive back the all-encompassing darkness, I just added a directional light, which basically acts like the sun. And a quick test reveals that it looks better. It doesn't look amazing, but it looks better than before. After these visual basics, I now added a new node that will act as the origin of the molecular dynamics simulation. Most of the logic of the molecular dynamics simulation is actually in the script that is attached to that molecular dynamics origin node. In the beginning, I just add some variables and constants that are needed throughout the script. For example, which atom type is currently selected, as well as a list of all the atoms that are currently active in the scene. And of course a dictionary that contains all the parameters for the Lennard-Jones interactions. Then we need of course a function that implements the Lorentz-Berthelot parameter mixing rules. You might have noticed that my parameters also contain a parameter called cutoff, which I didn't mention yet. This cutoff means the cutoff distance, which is the distance at which the force between two atoms is basically 0, so we can skip the calculation. And since I didn't find any literature on how to mix these cutoff parameters, I just made up my own rule. Then we needed a function that calculates the force between two atoms. There's not really much to say here. If the distance between the atoms is larger than the cutoff parameters, we immediately return the 0 vector. And for a slightly more efficient computation, we pre-compute the sigma over r term. Then I added the asset for the atoms, which is basically just a sphere. In the MD origin node, I created a function that enables us to create an atom at a given position. Then I added a script to our atom asset. These atoms will handle their own kinetics, so they need this script, but they should also offer some convenience functions, for example for changing the species, which involves changing the mass of the particle, the radius of the sphere as well as the color of the sphere. We make immediate use of the ability to set the species of the atom in the spawn atom function of the MD origin. Finally, we need a way to call this spawn atom function as a player, and to do this I add another script to the write controller and listen for pressed button events. If the press button is the trigger, then that script emits its own signal, which is called addAtom, which also delivers the position of the controller at the time of the event. And this signal can now be connected to the MD origin node, where the only action of it is to call spawn atom with the controller position as an argument. This employs the signal system of Godot, and I think it's kind of neat to decouple individual components like that. And now let's test it. And yeah, it works. We can now add spheres to our scene, which don't do much yet, so we still need to implement the actual dynamics. One function I would also like to implement is just the ability to clear all atoms to start with a fresh slate. And this function is getting connected to the grip button the same way as the spawn atom function. And this also works pretty nicely. Next, we define what happens in every physics tick of the game. The molecular dynamics node looks at all pairs of atoms and calculates the forces acting on each atom. Of course, we need to apply the parameter mixing rule beforehand. The atom class has a method to accumulate this acting force, so it basically sums up all contributions from the other atoms. Then we have to iterate over all atoms again and tell them to do the first part of the velocity whirlet step, which is to update their position. Before we continue with the other half of the velocity whirlet algorithm, let's implement the needed functions for the atom class. The function accumulate force just calculates the acceleration by dividing the given force by the mass of the atom and then adds that to a local variable acceleration. The function update position just applies the first step of the velocity whirlet algorithm and updates the position of the atoms. Update velocity performs the second part and, as the name suggests, updates the velocity of the atom. For that, we also need a second acceleration, which I very creatively called acceleration 2. Acceleration 2 also will be accumulated with its own dedicated function. After the velocity update, all accumulated accelerations are set to 0 since we are starting a new time step. And after fixing a bug or two in the code, we can actually observe very rudimentary dynamics working. I guess I never talked about the second part of the velocity whirlet update in the MD update function. But it is basically the same as the first half. We have to recalculate all forces, so we need to iterate over all pairs of atoms again. But this time accumulate the acceleration into acceleration 2 and not the normal acceleration variable. And then instead of telling the atoms to update their positions, we tell them to update their velocities. To make the simulation run a bit smoother, I changed a few things. First, the scale of the simulation. Currently the scale is probably that 1 meter corresponds to 1 Bohr. This means that a hydrogen molecule is more or less as big as an average adult human, which is quite large in my opinion, so I scaled it down by a factor of 2. Secondly, I also adjusted the timescale so that the simulation runs a bit slower and it looks smoother that way. And lastly, I added some friction terms which should slow down very fast dynamics. And I think with these changes, I think the dynamics look quite pleasing now. But we are not done yet. We also need the ability to change the element. First part of that is actually knowing what element is currently selected. To convey this information, I attached a text to the left controller. And then a function to change the text of the label. And then I had to connect a bunch of different signals. I want the left controller buttons to increment and decrement the element number, so I had to connect their inputs to the MD simulation. The MD simulation had then to tell the label what the currently selected atom is. Additionally, some more logic is needed to figure out the previous or next element in the list and rub around if necessary. All in all, I think it's not too interesting, but I wanted to mention it for completeness sake. And after some more bug fixes, we can now select the element that we want to add to the simulation, and it actually works fine. I don't want to spend too much time on this, but I wanted some more mobility, so I added some simple flight logic to the VR player. With this, I am much more mobile in the simulations, which make them quite a lot more enjoyable. It feels great having superpowers. And to finish off the project, I made everything look a bit nicer. I gave the ground some texture, I fixed the lighting and also added some texture for the sky, and now I think it doesn't look too bad. I have never used Godot before, but I was pleasantly surprised by how easy it is to get into it. Together with VR development, I can only recommend to try and create something yourself with it. It's really great designing a world and then being able to immersively experience your creation. I am sure you can do it because you are all smart people. While you ponder over the possibilities, I leave you with some more footage of the simulation, but this video is over now. Bye!